Hello everybody, my name is Zach Smerge and today I'll be presenting you an analysis and comparison of modern facial recognition algorithms. I'm doing this for my pattern recognition class at the University of Florida. This is spring 2014 semester. So facial recognition is an exciting and developing field that is advancing to the point of widespread adoptions. We see a lot of applications such as advanced video surveillance, a lot of social media like Facebook nowadays will do the auto tag for you. There's also a lot of secure trading terminals and just secure authentication purposes that it can be used for. And while this task does seem trivial for people, even infants can identify faces, creating an algorithm on a computer that can run with good performance and high accuracy is actually very difficult. So today we're going to look at three different schemes: eigenfaces, Fisher faces, and local binary pattern histograms. We're going to test on two different databases, the AT&T dataset, which is a smaller, simpler subset, and then the extended YaleB dataset, which is a larger and harder dataset to work with. We're going to test all three of these algorithms for various performance metrics. The things we're looking at today are the training time, so this is the time that it takes to train a single face. The testing time, so if you're giving a single sample, how long does it take to determine whether that face is recognized or not, and then the accuracy, whether or not it gets the face correct, so this will count false positives and whether or not it gets the answer wrong. So we'll start out with the eigenfaces algorithm. Just a brief overview here. The idea of the eigenface algorithm is to take the high dimensionality space of the image and convert it into a smaller set where it typically just looks for the greatest variances in the image. It uses the principal component analysis, which we'll refer to as PCA, to do this. A good example of how this would work is if you have a single image from the AT&T database, it would be a 92 by 112 pixels. You can see this is over 10,000 different dimensions for the image space. And so PCA will look at this and it will determine what the principal components are, the components with the largest variance. We'll choose a small subset, maybe 300 or so. And so the advantages are that it converts it to a smaller search space, and this makes it very simple and quick to compare against. The disadvantages are that the principal component analysis looks for the greatest variances in data, which are not always due to the face itself. They can be caused by external obstacles. And a good example we'll see later is lighting variations can cause a lot of external variation. And so this is just a sort of an example of a reconstruction using eigenfaces. And so the principal components, or the eigenvectors, shown here are anywhere from 10 to 310. And you can see in the first row, there's not nearly enough to provide the full face. But once you get to the third and fourth row, 2 and 300 eigenvectors are plenty enough to reconstruct the face. So this is a simple look at the algorithm. The first step here is to compute the mean for any vector in the image. Using this mean, we can compute the covariance matrix S, and from this we can get the eigenvalues and eigenvectors of S. Using these eigenvectors, we essentially take the k largest of them, and these are our principal components, and we can solve them from this equation here. And the x equals wy plus mu gives us the reconstruction for those, which we saw previously in the example. And essentially what it'll do is it'll train itself by finding the k largest principal components, and then every time it checks a sample image that it wants to test for a face, it will project the training samples into the subspace and use a nearest neighbor algorithm then to determine whether or not it is face A or face B, or not in the database at all. The Fisher faces algorithm is very similar to the eigenfaces algorithm. They used Fisher's classification to improve the eigenfaces algorithm. The idea here is that instead of just grabbing the greatest principal components, it actually does a class-specific reduction, and so it will choose features that separate best between the classes rather than the overall. And so basically this looks for the same classes should cluster tightly together while different classes should spread apart. The advantages are similar to the eigenfaces in that it's a simpler, smaller search space, but it also has the benefit that it is robust against external sources of variation, and we'll see that later on. The algorithm here is pretty simple to begin with. Once again, you compute the mean, and then using this you compute the between scatter matrices and within scatter matrices, designated SB and SW. Once we have these, we can do a similar projection into the subspace, and then we'll use this this W optimization algorithm, or I should say equation on the bottom, to determine whether or not the testing image matches what we have trained it with. The last algorithm we'll be looking at is local binary pattern histograms. This takes a much different approach from the eigenfaces and Fisher faces algorithms. What it does is it focuses on describing just the local features of an object. This is a type of texture analysis in which each pixel is compared against its neighbors to create a local binary pattern for each pixel. A simplified example of how this works would be if you had a single pixel that was compared against all its neighboring pixels. In this example, we can compare 54 in the center against all these external values. Anytime it's greater than or equal, you put a 1, otherwise you designate a 0 for less than. And then you get a representation which we call a local binary pattern. And then once we do this across the whole image, we get an entire histogram that we can compare against. The advantage here is that it's very robust against illumination changes specifically. If you can look in the example above, there's 4 separate images. It's the identical image, but they've changed the brightness by hand. And typically you would see a lot of different variations, but with local binary patterns, you can see that all 4 images, the histograms, are nearly identical. So that's a very strong advantage that the local binary pattern histograms have. The algorithm is pretty straightforward. Just like I was saying before, it's summation around the pixel based on that central pixel and the intensity around it. You use the sine function s, where 1 if x is greater than 0, else 0. And there's been some advancements too. I should mention that this is the advanced version of local binary pattern histogram. So given the point x and the position of the neighbor, it calculates xp and yp. Okay, so next we're going to move on to the databases. The 2 databases are the AT&T one first. This is the simpler data set, as I may have mentioned. There are very mild distortions, such as differing facial expressions, smiling or frowny face, small rotations on the head, as well as differing facial details, such as some wearing glasses or some not wearing glasses. In this data set, there's 40 separate people. Each person has 10 unique faces. All the images are 8-bit, 92 by 112 pixels, all grayscale and PGM format. And thankfully they've come cropped and sized for a full frontal view, so there's no manual labor done there. The extended Yale B-face database is a more complex data set and a little bit larger. The distortions are more advanced, especially the illumination changes are a lot greater, the rotations are a little bit more, and I'd say the facial expressions are also more extreme. And with this data set we have 38 people with 64 unique faces, so a lot more faces for each person. The images are fairly similar in format, 8-bit grayscale, a little bit more pixels, 168 by 192, PGM format once again. And once again they come in cropped and sized to meet our needs. So the setup for my project was done in using Visual Studio 2012. I leveraged the OpenCV 2.4.6 library to use their built-in algorithms. I created a testing code that essentially has 2 formats. The first is the performance mode. This pretty much is a whole bunch of for loops that goes through all the different algorithms and the number of tests, and it varies in each test the number of training samples. So there's a lot of tests there, and that takes a while to run. The second mode is a testing mode, which allows you to enter specifically which algorithm, which database, and the number of training samples you want to use. This is very beneficial for testing and debugging, but outside of that, it's pretty useless. And so, in order to get the training and testing functions, I simply started and stopped a timer before each function call, and so that was pretty clean and cut. The accuracy data is essentially averaged based on the number of testing samples for that run, and that's also dependent on the database that we're running it on. The accuracy data is a little complex because the number of testing samples changes depending on how many of the samples we're using for training. So essentially, if we only have 10 samples to use and we use 7 of them to train with, and that only leaves 3 to test with, so it kind of it's sort of dynamic depending on what test we're doing. Okay, so let's go look at some code. Over to Visual Studio. Once you get Visual Studio set up with OpenCV, it's pretty nice. So this is my main program. Go down here. Here are some constants for reading in the images. Once we enter in, the first one here is the test mode, where it allows you to input the values for the algorithm, database, and the cutoff. Given this, we can open all the images, create an output file. Once we get into here, we're going to start loading the images. Essentially, for the images, what we do is we put them all into a vector called face and person. And these pretty much say, this face belongs to this person. And using these 2 vectors, we can train our classifier here. And you can see we're starting and stopping the clock, so that's how we get our training time. We go down further into the testing phase. We read through all the faces and all the people that we have, and for each one we make a prediction with our model, and we compare this prediction to what we know it should be, and from there we determine whether or not it was correct or incorrect, and we loop this over all the pictures for the whole database. And once that's done, we can calculate the average prediction time and the average accuracy based on how many it got right out of how many total. Next part of the code goes into the performance test, and this increments over all the algorithms for each database and for a number of different cutoffs. And like I said, this test can take a long time to run. It's doing pretty much the same things, except it's aggregating it into multiple files. And so the code's pretty straightforward in that sense. I can just run we can see our debug priorities. And right now we're going to run 005 for our command line arguments, which you look here. 005 says we're running the eigenfaces with the AT&T data set, and we're going to use a cutoff of 5, which essentially means 5 samples for training out of 10, which means the other 5 will go for testing. And so if we run this program, it'll build real quick and run for us. All the outputs will go to an output file labeled accordingly. All it's going to show here is what you're running, what it's doing. It's loading images, it's training currently. And this is the eigenfaces running the AT&T database. This one shouldn't take too long because it's the AT&T database. Just give it a second here. And actually, I think I've run this before, so I can probably just open it up, but it should be done in a second. So right now it's just running through and testing all the samples. Test complete. So we can go over here, reload this, and in here it'll tell you, if you notice the name here is eigenfaces, the AT&T database, and the 5 samples for training. And so the first thing it tells you is the amount of time it took to train, which was about 27 seconds. And then it tells you the prediction time for every single image that it tested. And at the very bottom here, it'll tell you what the average time was, coming in at around 46 milliseconds. And it'll tell you the miss rate, which was 10%. It missed 20 images out of 200, which is pretty good. Now let's look at some results that we got. So this first set of results is the training time, and on the left you have the AT&T database, and on the right you have the Yale database. As far as training time went, depending on the number of samples, once we got to a more practical number of samples, which is around 7 or more, you can see that the eigenfaces especially start to really get up there. The Fisher faces grow a little bit more gradually, and the binary pattern histogram are really the best for training time. You can see they start out a little bit higher, but once we start to add more training samples, it really stays much lower than the Fisher faces and the eigenfaces especially. And so this test really just measured the time to train the classifier, and this is really a summation of what I just said, so we'll keep going. The next one is the testing time. Once again, you can see the AT&T on the left, the ELB on the right. And this sort of shows one of the problems too, is the AT&T database is so small, you didn't see a lot of the problems until you got to a lot more training samples, so you can see that in the ELB database. But as far as testing time went, it was pretty clear winners here, winners and losers I should say. The Fisher face is just much better with testing time compared to the eigenfaces and the local binary pattern histograms. Eigenfaces did good in the beginning, but got much worse as time went on. And so like I said, just summing up that real fast, Fisher faces much faster and more consistent. Local binary patterns lowest overall, but much more steady. Eigenfaces really jumping around. And so the last and probably arguably the most important is the accuracy graph. You can see here that it really depends on which database we're looking at. So when we look at a simple database like the AT&T database, once we got to 7 training samples, all 3 of these tests were really doing above 90% accuracy. All 3 of them did really well. And the eigenfaces led, which just by a tiny bit. Once we got to the harder database, the ELB, you can see that the local binary patterns really showed their strengths there. Especially with a lower number of training samples, it did much better. The Fisher face algorithm also did very well, depending, and the eigenfaces not so much. And this really shows that the Fisher faces implementation, how they improved the eigenfaces method, was very worth it. Overall, much faster and more accurate in general. Local binary pattern histogram has a lot of strength as well. It takes a little bit longer to do, but is well worth it, I think. So, in conclusion, the results we presented provide a basis for comparing different facial recognition algorithms. So if you had to decide on one to implement today, I hope that this would help. Overall, we saw the Fisher faces was the most well-rounded in terms of accuracy and testing times, and the local binary pattern histogram was coming in with a close second. It was very accurate, but it sacrificed testing time, so it depends on how quick you really need it. It's really the performance versus accuracy trade-off here, and the eigenfaces did the worst overall. Now there's a lot of future improvements here. The first thing to think about would be to incorporate more algorithms. There's a number of other things to do. There's geometric based, which is a lot more computationally intensive, and then similar to the texture analysis, there's the Gabor wavelets and the discrete cosine transforms, and there's others outside of this as well. Another thing that we could do to improve our test is to use more test data sets. We could use larger test sets, and we could also use more difficult tests that have different sources of variation as well. We could also expand the performance evaluation to incorporate other metrics. So today we tested the training time, the testing time, and the accuracy. We could also look at space allocation, so how much space is allocated during testing for these algorithms, how much space does it take to store the training set. I think those would be really good and useful to a lot of people. And another thing too, which I read about but I didn't really get into the details of, would be to explore which sort of samples are best for training a classifier. So we might determine that, you know, a smiling face, a frowny face, and an off-colored sample are, you know, the 3 best images, you know, something like that. So that's an interesting way to look at things, I think. So really a lot of future improvements that we could look at. And then if you're curious, there are a ton of references that you guys can go off of. Hope you guys enjoyed my lectures. Have a great day.